Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In my previous lecture video, I have discussed about origin of magnetization and its classification. In this lecture video, I will discuss about applications of magnetic materials. So let's get started. The content of this lecture video is as follows. I will explain about the applications of magnetic materials, mostly magnetic devices, which includes transformer cores, magnetic storage, and magneto-optical recording. First of all, let's understand what is magnetic core. A magnetic core is a piece of magnetic material with a high magnetic permeability used to confine and guide magnetic fields in electrical and magnetic devices such as electromagnets, transformers, electric motors, generators, inductors, magnetic recording heads, and magnetic assemblies. It is made up of ferromagnetic metals such as iron or ferrimagnetic compounds such as ferrites. The high permeability relative to the surrounding air causes the magnetic lines to be concentrated in the core material. The magnetic field is often created by a current-carrying coil of wire around the core. The use of a magnetic core can increase the strength of magnetic field in an electromagnetic coil by a factor of several hundreds times. An electric current through a wire wound into a coil creates a magnetic field through a center of the coil due to Ampere's circuital law. Coils are widely used in electronic components such as electromagnets, inductors, transformers, electric motors, and generators. A coil without a magnetic core is called an air core coil. Adding a piece of ferromagnetic or ferrimagnetic material in the center of the coil can increase the magnetic field by hundreds or thousands of times. This is called as a magnetic core. The field of the wire penetrates the core material, magnetizing it, so that the strong magnetic field of the core adds to the field created by the wire. The amount that the magnetic field is increased by the core depends on the magnetic permeability of the core material, because side effects such as eddy currents and hysteresis can cause frequency-dependent energy losses. Different core materials are used for coils used at different frequencies. Now let's see what is transformer. A transformer is a passive electrical device that transfers electrical energy from one electrical circuit to another or multiple circuits. A varying current in any one coil of the transformer produces a varying magnetic flux in transformer's core, which induces a varying electromotive force across any other coils wound around the same core. Electrical energy can be transferred between separate coils without a metallic or conductive connections between the two circuits. Faraday's law of induction, which was discovered in 1831, describes the induced voltage effect in any coil due to a changing magnetic flux encircled by the coil. Transformers are most commonly used for increasing low AC voltage at high current, a step-up transformer, or decreasing high AC voltage at low current, a step-down transformer, in electric power applications, and for coupling the stage of signal processing circuits. Transformers can also be used for isolation, where the voltage is equals the voltage out, with separate coils not electrically bounded to one another. The magnetic core of an electrical power transformer comprises primary, secondary, and tertiary windings, with primary windings on one side and secondary windings on the opposite. Magnetic flux in between is what connects them on the core, allowing current to flow. Here are some pictures which shows the different types of transformers. Now let's see what is transformer core. A varying current in the transformer's primary winding attempts to create a varying magnetic flux in the transformer core, which is also encircled by the secondary windings. This is varying flux at the secondary windings induces a varying electromotive force or voltage in a secondary windings due to electromagnetic induction, and the secondary current so produced creates a flux equal and opposite to that produced by the primary winding. In accordance with the Lenz's law, the windings are wound around a core of infinitely high magnetic permeability so that all of the magnetic flux passes through both the primary and the secondary windings. With a voltage source connected to the primary winding and a load connected to the secondary winding, the transformer currents flow in the indicated directions and the core magnetomotive force cancels to zero. Transformers feature primary, secondary and tertiary windings whose working depends on the flux that is produced between these windings. Magnetic core in transformers serves as the pathway of the flux. These cores are magnetic materials with high magnetic permeability used to guide magnetic fields in transformers and other electrical or magnetic devices. They are made up of ferromagnetic metals or compounds. The ideal transformer is shown in this diagram with induction law. According to Faraday's law, since the same magnetic flux passes through the both primary and secondary windings in an ideal transformer, a voltage is induced in each winding proportional to its number of windings. In this diagram, blue color winding is a primary winding, whereas the red color winding is a secondary winding. As the AC power supply V1 is given to the primary winding and V2 is given to the secondary windings, which produces primary leakage magnetic flux phi L1 and secondary leakage magnetic flux phi L2 respectively, and the magnetic flux phi M between primary and secondary windings will be generated. The transformer winding voltage ratio is directly proportional to the winding turns ratio. Now let's see the schematic of transformer core, which is shown in this diagram. When the AC power supply is applied to the primary winding of a transformer, the primary winding produces magnetic flux phi, which flows through the iron core of the transformer, and the magnetic flux cuts the secondary winding of the transformer. But all flux of primary winding does not cut the secondary winding. Some part of the flux, that is phi L1, completes its magnetic circuit by passing through the air rather than around the core, which is shown in this figure. This leakage flux is produced due to the primary ampere turn existing between point A and B. This leakage flux phi L1 completes the magnetic circuit in the portion AB. Hence, this flux is known as a primary leakage flux and is proportional to the primary ampere turns. This flux phi L1 is in time phase with primary current I1 and induces an EMF EL1 in primary winding only. Similarly, due to secondary ampere turns across points C and D, leakage flux is produced phi L2, which is linked with secondary winding only, not linked with primary winding. This phi L2 is in time phase with I2 and produces a self-induced EMF EL2 in the secondary winding. The both leakage flux at primary and secondary fully depends on the load of transformer. If load of transformer increase, leakage flux will simultaneously increase. The leakage flux linking with each winding produces self-induced EMF in the winding, and this EMF is equivalent to a small choker or the inductive coil in series with each winding. And the voltage drop in each series coil is equal to that produced by leakage flux. A transformer with to an ideal transformer is equivalent to an ideal transformer with the inductive coil connected in both primary and secondary circuits as shown in this diagram. Closed core transformers are constructed in core form or shell form as shown in this diagram. When windings surrounding the core, the transformer is core form. When windings are surrounded by the core, the transformer is shell form. Shell form design may be more prevalent than core form design for distribution transformer applications due to the relative ease in stacking the core around winding coils. Core form design tends to, as a general rule, be more economical and therefore more prevalent than shell form design for high voltage power transformer applications at the lower end of their voltage and power rating ranges, less than or equal to normally 230 kilovolt or 75 megavolt amperes. At higher voltage and power ratings, shell form transformers tend to be more prevalent. Shell form design tends to be preferred for extra high voltage and higher megavolt ampere applications because though more labor intensive to manufacture. Shell form transformers are characterized as having inherently better kilovolt ampere to weight ratio, better short circuit strength characteristics, and higher immunity to transit damage. Now let's see the types of cores in transformer. First is steel limited cores. Transformers for use at power or audio frequencies typically have core made of high permeability silicon steel. The steel has a permeability many times that of free space, and the core thus serves to greatly reduce the magnetizing current and confine the flux to a path which closely coupled the windings. Early transformer developers soon realized that core constructed from solid iron resulted in a prohibitive eddy current losses, and their designs reduced this effect with cores consisting of bundles of insulated iron wires. Later designs constructed the core by stacking layers of thin steel laminations, a principle that has remained in use. Each lamination is insulated from its neighboring by a thin non-conducting layer of insulation. The transformer universal EMF equation can be used to calculate the core cross-sectional area for a preferred level of magnetic flux. The effect of laminations is to confine eddy currents to highly elliptical paths that enclose little flux, and so reduce their magnitude. In figure left, eddy currents I, which is in red color, within a solid iron transformer core, right side, making the core out of these laminations parallel to the field, which is capital B in green color, with insulation between them reduces the eddy currents. In this diagram, the field and the currents are shown in one direction, but they actually reverse direction with the alternating current in the transformer winding. Thinner laminations reduce losses but are more laborious and expensive to construct. Thin laminations are generally used on high frequency transformers, with some of very thin steel laminations able to operate up to 10 kHz. Laminating the core greatly reduces eddy current losses. Interlude EI transformer laminations showing air gap and flux paths as shown in this diagram. You may be wondering as how the primary and secondary windings are wound around these laminated iron or steel cores for these types of transformer constructions. The coils are firstly wound on a former which has a cylindrical, rectangular or oval type cross section to suit the construction of the laminated core. In both the shell and core type transformer constructions, in order to mount the coil windings, the individual laminations are stamped or punched out from larger steel sheet and form into strips of thin steel resembling the letters capital E and capital L, capital U and capital I as shown in these figures. These lamination stampings, when connected together, form the required core shape. For example, two capital E stampings plus two end closing capital I stampings to give an EI core forming one element of a standard shell type transformer core. These individual laminations are tightly attached together during the transformer's construction to reduce the reluctance of the air gap at the joints, producing a highly saturated magnetic flux density. Transformer core laminations are usually stacked alternatively to each other to produce an overlapping joint, with more lamination pairs being added to make up the correct core thickness. This alternate stacking of the laminations also gives the transformer the advantage of reduced flux leakage and ion losses. EI core laminated transformer construction is mostly used in isolation transformers, step up and step down transformers, as well as auto transformers. One common design of laminated core is made from interleaved stock of E-shaped steel shades capped with I-shaped pieces, leading to its name of EI transformer. Such a design tends to exhibit more losses, but it is very economical to manufacture. The cut core or C-core type is made by winding a steel strip around a rectangular form and then bonding the layers together. It is then cut into two, forming two C shapes, and the core assembled by binding the two C halves together with a steel strap. They have the advantage that the flux is always oriented parallel to the metal grains, reducing reluctance. Now see second type of cores in transformer, which is solid cores. Due to the electrical conductivity of the metal, when a solid one-piece metal core is used in alternating current applications such as transformers and inductors, the changing magnetic field induces large eddy currents circulating within it. Closed loops of electric current in planes perpendicular to the field. The current flowing through the resistance of the metal hits it by joule heating, causing significant power losses. Therefore, solid iron cores are not used in transformers or inductors. They are replaced by laminated or powdered iron cores or non-conductive cores like ferrite. Powdered iron cores are used in circuits such as switch mode power supplies that operates above mains frequencies and up to a few tens of kilohertz. These materials combine high magnetic permeability with high bulk electrical resistivity. For frequencies extending beyond the very high frequency band, cores made from non-conductive magnetic ceramic materials called ferrites are common. Some radio frequency transformers also have movable cores, sometimes called slugs, which allow adjustment of the coupling coefficient and bandwidth of tuned radio frequency circuits. Here are few pictures of solid cores which are shown in the diagram. Now let's see third type of cores in transformer is toroidal cores. Here are the few pictures. This design is based on a toroid, the same shape as a donut. The coil is wound through the hole in the torus and around the outside. An ideal coil is distributed evenly all around the circumference of the torus. The symmetry of this geometry creates a magnetic field of circular loops inside the core, and the lack of sharp bends will constrain virtually all of the field to the core material. This not only makes a highly efficient transformer, but also reduces the electromagnetic interference radiated by the coil. Toroidal transformers are built around a ring-shaped core, which, depending on operating frequency, is made from a long strip of silicon steel or an alloy wound into a coil, powdered iron or ferrite. A strip construction ensures that the grain boundaries are optimally aligned, improving the transformer's efficiency by reducing the core's reluctance. The closed ring shape eliminates air gaps inherent in the construction of an EI core. The cross-section of the ring is usually square or rectangular, but more expensive cores with circular cross-sections are also available. The primary and secondary coils are often wound concentrically to cover the entire surface of the core. This minimizes length of wire needed and provides a screening to minimize the core's magnetic field from generating electromagnetic interference. Toroidal transformers are more efficient than the cheaper laminated EI types for a similar power level. Other advantages compared to EI types are include smaller size about half, lower weight about half, less mechanical hum, making them superior in audio amplifiers, lower exterior magnetic field about one-tenth, low off-load losses, making them more efficient in standby circuits, single bolt mounting, and greater choice of shapes. The main disadvantages are higher cost and limited power capacity. Because of the lack of a residual gap in the magnetic path, toroidal transformers also tend to exhibit higher inrush current compared to laminated EI types. Now let's see next type of cores of transformer is planar cores. A planar cores consists of two flat pieces of magnetic material, one above and one below the coil. It is typically used with a flat coil that is part of a printed circuit board. This design is excellent for mass production and allows a high-power, small-volume transformer to be constructed for a low cost. A planar E-core, a planar inductor, exploded view that shows the spiral tracks made directly on the printed circuit board are shown in this diagram. Next type of cores in transformer is pot cores. Usually ferrite or similar, this is used for inductors and transformers. The shape of a pot core is round with an internal hollow that almost completely encloses the coil. Usually a pot core is made into two halves which is fit together around a coil former, that is bobbin. This design of core has a shielding effect, preventing radiation and reducing electromagnetic interference. A pot core of RM type and a regular pot core is shown in this diagram. Now let's see the next application of magnetic material, that is magnetic storage. Magnetic storage or magnetic recording is the storage of data on a magnetized medium. Magnetic storage uses different patterns of magnetization in a magnetizable material to store data and is a form of non-volatile memory. The information is accessed using one or more read or write heads. Magnetic storage media, primarily hard disks, are widely used to store computer data as well as audio and video signals. In the field of computing, the term magnetic storage is preferred, and in the field of audio and video production, the term magnetic recording is more commonly used. The distinction is less technical and more a matter of preference. Other examples of magnetic storage media includes floppy disk, magnetic recording tape, and magnetic strips on a credit cards. Longitudinal recording and perpendicular recording, two types of writing heads on a hard disk, are important and are shown in these two diagrams. Now let's see in detail perpendicular or vertical recording as shown in this picture. Perpendicular recording, also known as vertical recording or PMR, perpendicular magnetic recording, is a technology which allows digital data to be stored on a hard disk surface, forming a high-density storage device. Professor Shunichi Iwasaki at the Research Institute of Electrical Communications, Tohoku University, Japan, first proved this technology advantageous for magnetic recording. An energized coil produces a magnetic field showed here in red. The magnetic flux focused to a sharp point causes the cell directly underneath it to be magnetized perpendicularly to the surface of the disk. The disk has a magnetic underlayer which conducts the magnetic flux readily. The gap between the sharp pole tip and this underlayer is where the magnetic flux is the most concentrated, thus readily establishing a magnetic cell on the top layer. When the current in the coil is reversed, the magnetic field and the poles also reverse. Hence, the cell underneath becomes magnetized in the opposite direction. Each cell can therefore represent a binary ones or zeros represented by the direction of its magnetic field. Now let's see longitudinal magnetic recording, that is LMR. Longitudinal magnetic recording is a conventional method of recording where the magnetic cells align horizontally along the surface of the disk, thus occupying more space. An energized coil produces a magnetic field established by the metal core. The flux focuses over the gap and the cell directly below the gap is magnetized. This principle is very similar to that used in the tape recording heads. Magnetic material is composed of small grains, each with a random shape and size. Due to this randomness, 100 grains are required to represent a cell, which can then be magnetized to represent a binary ones or zeros. The 100 grains limit is a theoretical limit, and any magnetization involving lesser number of grains would be unstable. It is the biggest enemy of magnetism because it causes the grains to realign randomly, thus losing the magnetism. The grains of magnetic media are so small that even thermal energy changes within the air can cause the magnetism to change. The longitudinal magnetic recording (LMR) is shown in these diagrams. Next application of magnetism is magneto-optical recording. Magneto-optical recording, or MO, is a method of sorting and retrieving data using a laser and a magnet. The drive laser heats the magnet surface to a high enough temperature, allowing the polarization of the disc to be modified with a magnet for more precisely written data. When data needs to be read from a disc, a laser of less intensity is used. A thin film of magnetic material, for example, amorphous terbium iron cobalt (TBFeCO), magnetic field is coated on the substrate over which the data is written. Magneto-optical storage combines two technologies to give a storage medium that has high data density, durability, and quick data transfer. MO drives write magnetically with a thermal assist and read optically. Magnetic materials have a physical property called a Curie temperature, above which they lose magnetization due to the complete disordering of their magnetic domains. The magnet's coercivity, which is its resistance to magnetization by an outside magnetic force, decreases as the temperature approaches the Curie point and is zero thereafter. To record data in a magneto-optical device, a laser heats up the media, decreasing the media's coercivity to a level that allows its magnetism to be modified by a relatively weak magnetic field. Once the data is written, the area then cools and the magnetic data is not subject to modification or erasure by magnetic forces encountered during our daily routine. A schematic diagram of a write in a magneto-optical recording drive is shown in this diagram. A typical structure of magneto-optical recording on disk is shown in this diagram. To read the data from the MO media, that is magneto-optical recording media, the drive do not use magnetic current induced in the heads by changing magnetic flux on the disk, as a hard drive does, but instead takes advantage of the Kerr effect. Because of the Kerr effect, the polarization of light will change when it is shined upon an area of the disk that is magnetized. Shining a beam of polarized light on a magnetized surface causes the polarization of the light to shift slightly, usually less than half degree. If the magnetization is reversed, then the angle of change in polarization, the Kerr angle, is changed as well. The change in direction of magnetization can be viewed as ones and zeros, making MO convenient for data storage. As shown in this diagram, the structure of magneto-optical media is in some ways similar to that of CD read-write media. But instead of changing the refractivity of the media when it is heated, and magneto-optical drive changed the magnetic flux of a small area of the disk. Now, how to erase the data? Erasing the data, magnetic field is applied to material in the opposite direction. The focus laser pulse hits the disk above Curie temperature and causes local heating to demagnetize the surface. The disk is again demagnetized and data written on in the form of magnetization is erased. This is the mechanism of how to read the data and how to erase the data in magneto-optical devices. Now let's see what is magneto-optical drive. It is a kind of optical disk drive capable of writing and rewriting data upon a magneto-optical disk. A floppy disk is a type of disk storage composed of a thin and flexible disk of a magnetic storage medium in a square or nearly square plastic enclosure lined with a fabric that removes dust particles from the spinning disk. Floppy disks are read from and written to by a floppy disk drive, that is FDD. A hard disk drive, that is HDD, is an electromechanical data storage device that stores and retrieves digital data using magnetic storage and one or more rigid rapidly rotating platters coated with magnetic material. The platters are paired with magnetic heads, usually arranged on a moving actuator arm, which read and write data to the platter's surface. Data is accessed in a random access manner, meaning that individual blocks of data can be stored and retrieved in any order. HDDs are a type of non-volatile storage, retaining stored data even when powered off. Hard drives use magnetic memory to store giga and terabytes of data in computers. Here are some pictures of a floppy disk drive, hard disk drive, and compact disk. This is all about magnetism, its basic terms and few applications. In my next lecture video, I will discuss about next topic from unit number 5, which is superconductivity. So please don't miss my next lecture video. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.